Today I will be covering the topic power quality monitoring. Continuing with the series of lectures on power quality, it is the responsibility of both the generating as well as the end user to ensure that we get clean power. The utilities provide us clean power and we in turn don't pollute it by using devices which create power quality problems. If we do so, in times to come, we may be given economic penalty. Like in the case of power factor, the penalty may be levied on us. Even though the penalty is not being levied, we are losing out badly because of equipment failure due to the overheating of various equipments like motors, transformers, etc. And also it is leading to unnecessary tripping and operational failures. The existing policy that we have got takes care of the power factor and voltage regulations, and it has been ensured very strictly at the user side, and the grid is also ensuring that we get reliable supply and the frequency is hardened. As discussed earlier, the power quality issues that we face are the transients, harmonics, reactive power, network unbalances, oscillations, voltage variations and flicker. These all combine together to create a problem which has to be addressed by each one of us. Now coming to category of power supply variations. The transients. Impulsive, they are from impulsive transients. They are from 5 nanoseconds to 0.1 millisecond of rise time, and the duration varies from 50 nanoseconds to 1 millisecond. Oscillatory transients, they are of low frequency, medium frequency and high frequency. They range from 5 kilohertz to 5 megahertz, and the duration is from 5 nanosecond to 50 milliseconds. Short duration variations. They are of 3 types: instantaneous, momentary and temporary. Instantaneous is from 0.5 to 30 cycles, momentary is from 0.5 cycles to 3 seconds, and temporary is from 3 seconds to 1 minute. Beyond 1 minute, it is called long-term voltage variations. They are characterized as interruptions or breakdown or under voltage and over voltage. Now the power quality standards have been very briefly given by Central Engineering Authority. They are as follows. Frequency should be close to 50 Hertz. In our case, 49.2 to 50.3 Hertz. We have to maintain a maximum and voltage. We have to maintain a voltage limit. Maximum and minima are as shown. For 33 kVA, it is from 30 to 36 kilovolt, and for 765 kV, it is from 800 to 728 kV. Temporary over voltages. For 132 kVA, we can have a system that has to be designed up to 170 kV peak voltage. Percentage of maximum voltage unbalances. From 33 kV to 132 kV, we can have a voltage unbalance of 3, and it reduces in higher voltages up to 1.5%. Voltage waveform quality or harmonics. At our level of 132 kV and below, the total harmonic distortion allowed is 5%, and individual harmonics of any particular frequency, whether it is positive, negative or 0, should be not more than 3%. For 132 kVA and below, we can have a total harmonic distortion of 5%, and individual harmonic distortion, whether it is positive or negative sequence, they should be not more than 3%. Now the CA has instructed the NLDC and SLDCs to introduce power quality meters in the utility side. It is slowly being monitored. Our electric supply bills which come to our to higher utilities show the number of breakdowns that are happening and what are the causes for it. Till now we are not being asking justification. However, in times to come, the power quality as well as the breakdown responsibility of the user will be excised, and we will have to take responsibility for the same. And in the distribution side, the low voltage variation that allowed is plus minus 6%. All states are yet to come out with a formal policy or a uniform policy, and this varies from state to state and they are generally following the European standards. High voltage variations that are allowed are plus minus 6% to 9%. Extra high voltage is 10% to minus 12.5%. In case of harmonics, we can have in terms of harmonics, the THD allowed is 5% and it is also 3%. Voltage imbalance, again, it is maximum of 3% that is allowed. These Indian standards are yet to be formalized. However, we are generally following the European standard 50610 and the broad guidelines, and in times to come, this is likely to be implemented in the states also. 50 Hertz is the frequency and the variation allowed is 1%, and in a weak system it is allowed up to 4 to 6% variation. The magnitude of supply with the normal voltage, we can have variations up to 10%, and rapid voltage variations we can have up to 5%, and in medium and low voltages we can have from 4 to 6%. Voltage dips that are allowed are up to as low as 60% for a duration of less than 1 second. Number of voltage dips that are allowed are in the tune of 1000 per year. Harmonic voltages, it is 5% for positive sequence and 6% for negative sequence and 2% and below for zero sequence network. Overall, the THD should be less than 8%. Voltage unbalances should be up to a maximum of 2%, and in certain locations up to 3% is being allowed. Short-term interruptions not more than 20 to 50 per year for a duration of less than 1 second. We can have temporary over voltages up to 1.5 times and transient over voltage of up to 6 times the RMS value. These are the European standards which are these are the European standards and which are likely to be implemented in India also. Now coming to power quality analyzer. The power quality measurements give a big insight into how we can visualize and understand our systems. We had used the Motwana MPQ 3033. In my case, the power quality analyzer used is MPQ 3033, which gives us insight into the substation. After connecting the 4 probes, that is the neutral and 3 phases, to the substations, in this case it was connected in CME, we realized that we had a neutral voltage. If you see both the slides, you will realize that the neutral voltage is changing depending on the load. That clearly shows the system is not balanced. In harmonics, we had a maximum of 1.98 when measured once and 1.75. So the total harmonic distortion in the system is within the acceptable limit for CME. Power factor. While measuring, we realized that the power factor was shown as 0.642. However, after taking the readings again, we got an acceptable reading. This shows that the power quality monitor or any analysis should be done over a period of minimum 1 week to get a realistic figure. It also shows the phase angle between voltage and current. Now coming to voltage imbalances. We can see in our case there is a slight voltage imbalance while taking the measurement both times. So we have to redistribute our load. Voltage dip oblique swells. The power quality analyzer clearly brings out the voltage dips oblique swells in the system. Hence, we know where the switching or any power electronic device is being used and they can be effectively countered. This again emphasizes that there is slight variation in the sinusoidal waveform. That means there are certain harmonics that are injected into the system, for which we have already taken the measurements. This can be corrected. Hence, from the figure we can realize and visualize that we have to put certain power quality. Hence, this slide shows the dips oblique swells in the system. The waveform is not pure sinusoidal and there are certain flickers in the system. Hence, we know that we have to use power quality conditioning at some stage when we have to use certain power quality equipments so that these waveform can be as close to sine wave as possible. Hence, we realize that hence we can conclude that having a power quality analyzer will give us a good understanding of the power quality that a substation or a big station is having, and we can improve upon it and take corrective action and timely action. The solution can also be found which is optimal both by analyzing and arriving at with the help of power quality analyzer, we can find the correct and optimal solution because we are able to visualize the various facets which the power quality issues are being faced by a station or a substation. Now we can conclude. In the following few slides, we have seen the power quality standards which are not uniform across the states, as well as the nation is still to come up with a power quality standard. However, the complete infrastructure in place to do the same. The use of power quality analyzer, we are able to visualize the various problems that a station is facing, and we can come up with an optimal power quality solution. Thank you.